So we are going to start a new chapter today, which is one of the most important chapters in the course. And today we will discuss the motivation. This class is important. So this class is about process synchronization. So based on what we have discussed till now, yes, we have understood these things that processes can execute concurrently. It's at one point of time only one process executes, but different processes are executing at different point of time. More importantly, a process can be interrupted at any time due to context switch. So at that point, you cannot say exactly when, or you cannot predict exactly when a process would be interrupted. So maybe at any point of time, it can be interrupted due to a context switch and some other process can run. Later, that process will, this process which was interrupted will be resumed again from that point where it was interrupted. Now, as long as we have just one process which is independent of all other processes, it's fine, because the kernel will remember that when exactly a process was interrupted and will resume it exactly from that point. So that part is handled by the kernel. How? By saving the registers and then again say loading the PCB, uh, loading the values of the registers into the program counter, stack pointer, and so on. Right? So that part is handled by the kernel. The problem arises when we have multiple processes which are cooperating. For example, we discussed last week about, or 1 week before, about producer consumer problem. So there we have a shared buffer, a shared memory, and a producer process and a consumer process are writing or reading from that memory. Such cooperative processes which are accessing the shared data, if we have that kind of a situation, then we need to be careful. Because, suppose we think that, okay, the example will just come, a detailed example. But essentially, because we cannot predict when a process will be interrupted or swapped out of the CPU, because we cannot predict that, this kind of multiple processes accessing the same shared data might lead to inconsistent situations that we will describe for an example. And in this chapter or in this topic, we are mainly considering how to avoid such inconsistencies. So we will discuss some mechanisms to ensure that even cooperating processes, even irrespective of when they are interrupted or context switch occurs, irrespective of all this, cooperating processes do work as expected. So first, let us understand the problem, and then we will talk about solutions. So again, let's talk about the producer-consumer problem, which I hope you remember. So there is this shared buffer. We implemented it as a circular queue, and there was one process which was the producer and one process the consumer. There used to be some pointers like say in, out. So in was the place where the producer will write the next item, and out was the position from which the consumer will read the next item. Also, we had this integer counter that keeps track of the number of full buffers. So we discussed that these variables, like the circular array itself, then in, out, counter, all these are the shared memory. So they are shared between the producer and the consumer. And this counter is initially set to 0. Every time the producer adds a new item to the buffer, it increments counter by 1. And every time the consumer reads an item from the buffer, it decrements counter by 1. Okay, so I hope you remember this producer-consumer solution that we discussed. So this was the pseudocode. So a producer will produce an item, then it will check while counter equal to buffer size. So if counter equal to buffer size, it means that the buffer is full. It should wait. right? So remember the semicolon here. So as long as this condition is true, it does nothing. Next, it writes the next item in the position in, and then increments in, and then says counter plus plus. Similarly, the consumer first checks whether counter is 0. If counter is 0, it waits. If counter is positive, then it reads or consumes the item at the element buffer and increments buffer, and then it reduces counter by 1. So we discussed this, and this is a correct solution of the producer-consumer problem. Like theoretically, it's a correct solution of the producer-consumer problem. Also, it allows us to use all the elements of the buffer. So theoretically, this is the correct solution. Let me say long back when, like long back in computer systems, when this kind of preemption was not there. That means a process would be allowed to execute on the processor as long as it does not voluntarily give up the CPU. In those kind of systems of old days, this would be fine. However, with the modern architectures where we are allowing like any time preemption, where we are allowing preemption, that means a particular process can be, deallocated the CPU at any point of time. In these kind of modern architectures, some problems can arise in this solution. For this, focus on these two steps, this counter plus plus for the producer and the counter minus minus for the consumer. The key thing to note here is that these two steps are not implemented as just one instruction. Okay. So if you come down to the assembly level, the program will be compiled and you will get some machine instructions. Counter plus plus can be implemented as these three instructions. So counter, the value is in shared memory. First load it into an array. First load it into a register, say R1. Then add 1 to that register value and then store back register 1 value to the memory. Similarly, counter minus minus could be implemented as these three steps. Right, so counter essentially is a shared memory variable. We know that, and first the value would be read from memory to the register. Then whatever changes to be made would be done, and then the value would be written back to the memory. Now, if we assume that kind of an architecture, now see some strange things can happen. Remember, a process can be swapped out or context switched at any point of time. So suppose we have S0 and S1. We have producer and the consumer. So producer at some point says counter plus plus and consumer at some point says counter minus minus. But then let's assume that this happens, this sequence which is written in the slide. First, producer executes register 1 equal to counter. Right? So the value of the counter, current value in the memory is loaded to register 1. And then producer executes register 1 equal to register 1 plus 1. So inside the producer, now register 1 is 6. Okay, let's say counter was 5 initially. So now register 1 is 6 for the producer. But just after this step, the producer was context switched. Okay. So it stopped and all these register values were saved by the kernel. Now let's say the consumer starts running. Consumer executes register 2 equals to say counter. So the value, again, the current value of the counter in memory is read to register 2. But then what is the current value of the memory? 5. Because though the producer had incremented the register, it did not have the time to write this value back to the memory. It got context switched before that. Okay. So if you consider the value saved by the producer in the register, it is 6. Register 1, it's 6. But this value has not been updated in the memory yet. So now when the consumer starts executing and reads the value of counter from the shared memory, it again reads 5. And then it does, let's say, it decrements the value of the register. So now register 2 for the consumer becomes 4. Okay. Now let's say again a context switch happens. The consumer is moved away from the CPU and the producer again executes. The producer has already done these two steps, load and add. So next step, of course, we know every process, when it resumes after the context switch, it resumes from the next instruction. Right? So, I mean, the instruction just after the one where it was context switched. So naturally, the producer executes the next instruction, which is to store back the register 1 value to counter. So in the shared memory, the counter becomes 6 now. Next, again, the producer is the context switched. The consumer starts executing. Consumer also had done these first two steps. So now it writes back the value of register 2 to the shared memory, which is now 4. So at the end of all these steps, we find counter equal to 4, which is not what the producer expected. From the perspective of the consumer, fine. Initially count was 5, now it is 4. But think of the producer, that will be disturbed. Because according to the producer, the value of counter should have been 6. Now it has become 4 in the shared memory. So next time when the producer tries to read the value of counter from the shared memory, it will get 4, whereas the correct value would have been 6. Such situations are called race conditions. They happen because of two factors. One is that the instructions that we think are just one step are actually not one step. Lower down, if you go down into machine level instructions, individual instructions that we write in the high level programming language are broken down into multiple machine instructions. That's one reason. And second reason is a process can be interrupted, or a process can be moved out of the CPU at any point of time. It is not possible to say exactly when it will be moved out. Okay, so that is the problem of race condition. Now it is important to understand this problem. So if you have any questions, then ask. Okay, good that everyone is following. So yeah, they said also this was a producer and a consumer. Same things can also happen in a parent-child scenario. So let's say the parent has forked a child. Now once that child has been forked, there are two processes, and we cannot assume that which one will run first. So if it happens that the producer and child, the parent and the child are sharing some data resources and all, again rest conditions may occur if we are not careful. So what is a rest condition a bit more formally? It is a condition where the outcome of the execution depends on the exact order in which the instructions that are spread over multiple processes get executed. Right? So going back to the previous slide, these instructions were actually spread over two processes. On the exact ordering in which these instructions were executed, that finally defines the shared value counter. This is a race condition, and this might lead to strange situations because we can never predict the exact order in which the instructions in different processes will get executed. Instructions in the same process, we know the order. But if the value of a variable or something depends on instructions spread over multiple processes, then we cannot be so sure about the order in which those instructions get executed. So this is the problem, the race condition. Now, henceforth, we will discuss solutions to that problem, which are known as process synchronization techniques. By the way, in this whole discussion, we will talk about processes like process synchronization. Understand that the same things can occur, same situations can occur in case of threads. So threads also have the same problem if multiple threads are updating the same shared variables, and very similar solutions are applied. Right, so we will go on talking about process synchronization, but internally understand that thread synchronization is also equally important, and similar mechanisms work there also. Okay. Now let us define some terminologies which are used to define the problem formally. Formally, this problem is known as a critical section problem. So consider n cooperating processes that access shared data. That is why they are cooperating. Each process has a critical segment of code. And the critical section is that part where the process is modifying the shared data. That is updating a common variables, updating a table, writing a file, which other processes are reading, etc., etc. So understand that the process might actually be the code might actually be quite long, and in many parts of the code, maybe the process is working on non-shared data, I mean local variables, etc. Those parts are not so critical. The critical section is that part of the code which actually modifies shared variables, shared data. Okay. So let's assume that all these cooperating processes, they have the same, all these cooperating processes, they have a critical section. So each process has a critical section. The basic requirement is that while one process is executing in its critical section, no other process is allowed to execute in its critical section. Okay. While one process is executing in its critical section, no other process is allowed to execute in its critical section. Okay. Any questions at this point? Otherwise, I have a question. Okay, let me ask my question. I mean, what is being said here? So we know that at one time only one process can execute. So when one process is executing its critical section, naturally no other process will be executing. So what is being said here? Isn't it stating the obvious? Okay, Deep is talking about multi-core, but no. Again, in this course, we are in this basic operating system course, we are not talking about multi-core architectures. We are talking about uniprocessor systems. Okay, please keep yourself muted, everyone. If you want to say, just say that I want to answer. I can give you a chance to talk. Okay. Okay, Ashutosh is telling the single line of code when translated to assembly may yield more than one instruction. That is what we saw in the previous couple of slides. All those instructions should be executed together. No, that is not what is being talked about here. In one sense, what Ashutosh is telling is right. We will come to that. But here we are not talking about that point. Because again, understand that a critical section may not be just one line of code. Maybe there is a shared array. So you are a processor is having to do several operations. Maybe multiple elements of the array are being updated and so on. You cannot expect that all these operations, like say in a shared memory, in a shared array, a process is updating 10 variables. Now you cannot say that, oh, updating all these 10 variables should be done together. right? That you cannot say. Even if you can say, okay, one variable updation should be like all these machine level instructions which are required to update one variable, that has to be done together. Okay, you might still claim this, but like a critical section can actually be quite long. Maybe 10 shared variables need to be updated, right? So yeah. Okay, Deep is saying preemption interleaves various plus execution. So Deep, unmute yourself and tell us what do you mean?
Sir, so like say there are two processes, both have a critical section and one has started executing it. It may get preempted in the middle of its critical section while it is handling shared data,
Mhm.
and the CPU may run the other process. And so the shared data was in an inconsistent state or in a state where another process should not see it, but the other process started working on that same data in its critical section. So that is not allowed.
Right, exactly. Good. So this line here, which is written in red here, this specifically means what Deep said. Two processes will not execute exactly at the same point. That we know. What is being told here is that suppose one process has started executing its critical section. After some time, it got preempted. Okay, we are talking about two processes in this set of cooperating processes. Okay. Now, yeah. So suppose process P0 has started executing its critical section. It executed a few instructions in the critical section, then it got preempted. Then some other process ran, etc. At some point, P1 was scheduled. So P1 is also in this set. Now, even though P0 is not running, there should be a mechanism that since P0 had started working on its critical section, P1 should not be allowed to proceed to work on its critical section. Okay. So at this point of time, the P0 is not running. P1 has been scheduled the processor. Even then, there should be some mechanism that since P0 earlier had started working on its critical section and it has not finished yet, P1 should not be allowed to work on its critical section. Right? So yes, still at a time only one process will execute. However, if any one of this process in this set, if any one of these processes has started its critical section and then got uh, interrupted or preempted, no other process in this set should be allowed to work on its critical section, even though it is allocated the CPU. I hope the distinction is clear. Like, uh, it's not about two processes executing simultaneously. That cannot happen in a uniprocessor system. But this is what we are getting at. Okay. If it is not clear, then ask. Okay. So the critical section problem is to design a protocol to solve this. Right? So this is the way we think of a process PI. It will be an infinite loop, let's say. Now there will be these two sections in the code, critical section and remainder section. Remainder section is not like in the remainder section, the process is not updating any shared data. It is working on local variables and so on. So it's okay. I mean, there is nothing critical about it. But this critical section is the part where the shared variables are being updated. So before this critical section, there will be an entry section where, if you understand, okay, so before this critical section, there will be this entry section, and right after the critical section, there will be the exit section. Okay, so intuitively, what will happen? In the entry section, PI will give some indication that I am starting my critical section. Okay, then it will execute this critical section. After that, it will give some indication that I have now completed my critical section. So others can also go into their critical section. But as long as PI is in its critical section, no other process in that set, in that cooperating set, should be allowed to enter its critical section. And that includes the time when PI is not executing. So suppose PI has started the critical section, but then it got preempted. So PI is not executing now. Even then, no other process in that cooperating set should be allowed to start on its critical section. Okay. Now, there are several conditions which need to be fulfilled for a correct solution of this critical section problem. There are basically three conditions: mutual exclusion, progress, and bounded waiting. Let's understand this. Till now, what we were discussing, that is actually the mutual exclusion condition. So if process PI is executing in its critical section, then no other process can be executing in their critical sections, even if PI is not assigned the CPU at this point of time. Okay. Once PI has started executing its critical section, no other process in that cooperating set should be allowed to execute in their critical section. This is what we were discussing. But there are two other conditions: progress and bounded waiting. What is progress? If no process is executing in its critical section, and there exists some process that wish to enter their critical section, then the selection of the processes that will enter the critical section next cannot be postponed indefinitely. Right? Essentially, what this is saying is all cooperating processes should be allowed to progress. Like, sure, if one process is taking a long time in the critical section, then the other processes have to wait. That's fine. But if no process is executing in its critical section, and there exists some process that wish to enter their critical section, then okay, let's say no process is executing in its critical section, but there is a particular process, say P5, that wishes to enter the critical section, then P5 should not be delayed indefinitely. Okay, P5 should be allowed to enter the critical section eventually. I mean, it cannot be postponed indefinitely. Quick question: how is this progress maintained? Just from what we have discussed. I'm not asking about any algorithm or anything. I mean, in the previous slide which we saw, which part is important for this progress? And if you have any questions, then ask, because it's important to understand these concepts. What is important for progress? Okay, one thing is that the exit section is, yeah, okay. So Deep, again, unmute yourself. What do you mean to say?
I mean, you said what is essential for success. So progress, as in if say one process gets stuck in its critical section, then no other process will make progress because they're all stuck at the entry of the critical section. So the one that is actually start working on the critical section should actually finish.
Yes, that's the thing. So the process which has been allowed to execute its critical section should finish, and it should give some indication that it has finished. Otherwise, the other processes will continue to be blocked. So let's say a particular process, it finished its, so say a particular process, say P1, P1 was allowed to enter its critical section. It completed the critical section, but did not indicate that. So the exit section somehow was forgotten. Then that creates a problem because P1 has completed its critical section. So no other process is now currently in the critical section. But others are not getting a chance to enter the critical section because P1 has forgotten to indicate that my execution of critical section is complete. That should not happen. So a process which gets a chance to execute the critical section should actually give, after completing it, should give some indication that I have completed my critical section, so that other processes waiting to enter the critical section can progress. Okay. The third condition is bounded waiting. A bound must exist on the number of times that other processes are allowed to enter their critical section after a process PI has made a request to enter its critical section. Okay. So it should not be that a particular process is starving. So it has made a request to enter its critical section, but continuously other processes are given a chance to enter its critical section and this process is ignored. That should not be the case. Okay. So yeah. So I mean, from the time when say PI has made a request and the time when that request is granted, that means PI is allowed to enter the critical section. How many times some other process is allowed to enter the critical section in preference to PI? That number should not be too large. There should be a bound. Okay. Of course, here we assume that each process executes at a non-zero speed. That means we don't assume, I mean, we assume that a process will not enter the critical section and be stuck indefinitely. However, there is no assumption contained in the relative speed of the n processes, right? So, I mean, you cannot assume that one process and every process moves I mean, more or less in the same speed and so on. So there's no assumption concerning relative speed of the n processes. This is important. Like in any scenario where multiple processes are cooperating, this assumption contained concerning relative speed is important. So like back in the producer consumer problem, we assumed that one may be faster than the other. So it may happen that the consumer takes a lot of time in consuming an item, but the producer is very fast in generating items. So then we had a mechanism that the producer can be stopped. Like if, say, the producer is putting on items in the buffer very fast, but the consumer is not able to consume so fast. So at some point, the producer should understand that the buffer is full and it should not put any more items. So basically we are not assuming that the producer and the consumer process progresses at the same speed. Right? So no assumption concerning the relative speed of the end processes. That is important. Even in your networks course, you will find this, like the sliding window protocols. And so there are ways in which a consumer can tell the producer that I cannot keep up with you. Stop, like slow down. Okay? So yeah, I mean, you should not assume while designing systems, you should not assume that all processes run at the same speed. Okay, coming back. Yeah, so correct solution to the critical section problem should not only ensure mutual exclusion, but also ensure progress and bounded waiting. Okay. Fine. By the way, just one small thing here that there are two types of operating systems designs based on whether a process is allowed to be preempted while it is running in kernel mode. Okay. So we know that a process can run in user mode, and when it makes a system call, let's say, then it runs in kernel mode and so on. Can the process be preempted when it is running in kernel mode? This is a question which for the OS designers to handle. Sometimes it is I mean, it is required that a process running in kernel mode should not be preempted, right? So yeah, I mean, here we are not talking, so, and that is because when a process is running in kernel mode, some kernel data structures are getting updated. Let's say a system call has been made, so some part of the kernel is actually running on behalf of the process, and some kernel data structures are being modified, possibly. So if it is allowed to preempt, if 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 I mean the process is allowed to be preempted now, even the kernel data structures can get garbled if we are not careful, because a rest condition can happen. So whether or not that is allowed, that is for the designers of the OS. Okay. We are not discussing that part, but just to. Okay, so now we will discuss different solutions to the critical section problem. And actually, we will discuss several solutions. So like over the next 2 or 3 classes, we will continue discussing different solutions to the critical section problem. Because this is one problem which is important in OS. Because we want processors, threads to cooperate, but we do not want to get into those conditions. Okay. So let us start with the first simple solution called Peterson solution. So this is a pure algorithmic or software-based solution. Okay. But it is restricted. There are several restrictions and limitations we will see. So this solution is restricted to 2 processes that alternate execution between their critical section and the remainder section. Okay. Give me a minute. Okay. Given that it's 9:50, almost 9:50, this will take some time, and there is no point in breaking this up into classes. I suggest that we stop here today. If you have any questions, ask. We will continue next class from this Peterson solution, because discussing this will take maybe 20 minutes of time. So no point breaking in between. Context switches create problems. So yeah, if you have any questions, ask. Otherwise, we can stop here today. So just to summarize, we discussed today about the rest conditions. And essentially, those are caused because of 2 reasons. One is that in individual instructions that we write at a high-level language, high-level programming language, actually they are broken down into several multi-level machine-level instructions. That's one reason. So just when we say counter plus plus, that is not actually one instruction. So it can be broken down into 3 or 4 instructions. The second reason is that we cannot say when a process will be interrupted or preempted from the CPU. So it can happen that we just wrote counter plus plus, but that got broken down into 3 machine level instructions. After executing 2 machine level instructions, the process was preempted. Right? So those things causes, I mean, these situations can cause race conditions. So we want to prevent that, and that is what we're going to discuss. So different solutions to the critical section problem. Fine. So if you don't have any questions, let's stop here today. We will continue next week. Thank you.